It is section 5.6, definite integral substitutions and the area between curves. Okay, let's see the theorem. A similar one was considered when we study substitutions in indefinite integral. With the substitution you call g of x, and without lower and upper bounds, and integral f of gx times g prime x dx is same as integral f of du. We know that. Now with lower and upper bounds ab, now we have to get here lower and upper bounds, but these are value of g at a and b. Let's see how we can get it. Here in proof, capital F is any antiderivative of f, then, and from the chain rule, we can get f of g, capital F of g, that is antiderivative of that. And we evaluate from A to B. From the second part of fundamental theorem of calculus, we can get it. Now the values are f of gb minus f of ga. We can rewrite this one in this form. Rather than g of x, we can put here u, and u is g of b on the top, and u is g of a on the bottom. Then this one can be written in this form. So we got that here. Now the new limit g of a and g of b are values of u equal f is g of x that correspond to x is a and x is b. Now when you are working on definite integral, then after getting antiderivative of f of u, you don't have to replace u by g of x. Just simply, after getting here antiderivative, you are using just the value g of a, g of b, just values so that you can evaluate quite easily. Okay, let's try to solve this problem. Okay, here. And now apparently, if we are using substitution for this portion, this group, then the problem will be changed to quite simple. Here, okay. Now u is here x to the 5 plus 2x. Then du. Okay, let's try to make u a little bit larger. Du equal g prime, 5x to the 4 plus 2, and here dx, right? Okay, so this portion and that portion will be du. Okay, now the lower bound, upper bound are for x. X is varying from 0 to 1. Now we have to find the lower bound and upper bound for u. So here, x equals 0 is, okay, let's try to use here that arrow. X is 0 means that u is 0. Here, if you're putting x equals 0, then u is 0. Now, x is 1, then u is now 3. So the given integral is same as, now it is u integration, so it must be from 1 to 3. And this portion is square root of u to the half power, and the remaining part is, we already know, that is du. Now, antiderivative of that one is the same as by adding 1, so 3 over 2. So reciprocal is 2 over 3, and u to the 3 over 2. Now u is from 1 to 3. So that here 2 over 3 is there, and that is now 3 times square root of 3, and power 3 over 2, and 1, that is 1 subtraction, right? Okay, now let's go to one more problem. Here, if we use u equal cosine x, then it is related with now du. Okay, let's check that. U is cosine of x. Then here du equal same as minus sine x and dx. Okay, so sine x dx is same as minus du. Okay, now we have to find the lower and upper bounds. Is x is moving from 0 to pi. Once x equals 0, then here u equal cosine 0, which is 1. Now, if x is pi, then cosine pi, u is cosine pi, and so that's a minus 1. So here, the given integral is changed into the corresponding g value at x equals 0 is 1. Now, the corresponding value of u for x equal pi is minus 1. So you have to keep here 1 and minus 1. You cannot put here minus 1 and 1. Okay. Now, okay, 30 is there, and cosine x is u, so there is u squared. And then now, okay, x sine x is the same as minus du. Okay, so along with this minus, and we can change here and lower bound and upper bounds. So if we write down again, then it's minus 1 to 1 and 3u squared du. So it is now u cubed and from minus 1 to 1. When u is 1, then the value is 1, minus 1, and minus 1. 1 minus minus 1 is now 2. Okay. Okay. Here, we consider this one in terms of change of variable. Okay, the substitution is making now along with u equal g of x, you can get this one. Now, lower bound and upper bounds are duly decided so that the interval and interval length will be changed. Due to change in the interval length, it requires a certain scaling. The reciprocal of g prime can be viewed as a scaling factor. In this new integral, it disappeared. So that basically 1 over g prime is multiplied in a sense. So it is a sort of a scaling factor. This subject will be treated in terms of change of variable when you study multivariable calculus in chapter 15. Here, let's see one example related with this remark. Let f of x is 2x for the definite integral of f over 0 and 1. Let's use the substitution u is 2x. Then we can write in this way. Integral from 0 to 1, 2x, that's fx dx. Now we are using u substitution, u is 2x. Then du is 2 dx. So that, and also, now once x is 0, then u is 0. Now once x is 1, then u is 2. And here 2x is u, and dx is half du. So we can rewrite it in this way. And now u is a sort of a dummy variable, so that we can change u by x. So here, let's try to evaluate the integral by interpreting it in terms of areas. Okay, so by using picture, let's try to evaluate both sides. Okay, the left one with the green highlighted. Okay, here the problem is the integral is now from 0 to 1. Okay, 0 to 1, but y, the height is 2x, so that is 2x, like that. It's increasing, and like that. So the height over there, when x equals 1, that is 2. So that we have to get the area. This area is definitely, we know that there is 1. Here, bottom length is 1, height is 2, divided by 2. So the area is 1. We can get it. Now, how about for that one? Now, the interval is expanded from 0 to 1 to 0 to 2. So we have 1 and 2, like that. And now half x, then when x is 2, the height is 1, so that here we have that 1. So we have to get, this is representing area of that one. So now bottom length is 2, height is 1, and divided by 2, so that again the area is 1. So even though the interval is changed, because of this scaling effect, we can get the same result. So later on, you learn it really with the details. But now we try to use the technique here explored in this example. Okay. Okay, we have recall here. Earlier in calculus 1, you learned that here the function is even when f at minus x is same as fx, and odd if f minus x is minus fx. That means that here even is symmetric with respect to y-axis. Here pictorially, the value at x and the value at minus x are the same. If it is positive here, then same height, so that the value over there, so that if it has this shape, then now right side again that shape, so that they are reflected with respect to y-axis. Now other function means that okay, let's make another picture. At x and minus x, okay, that is x and minus x. If it is a value and positive, then the other side, the value is negative. So that here, other function has property passing this one origin, and if it is given in this way, then now that is coming down. So once you try to rotate and 180 degree, and with respect to the origin, then it matches each other. That is called other function. Okay. Now, with that properties here, if we try to get integral, definite integral over symmetric interval minus a to a, then here once f is even, then minus a to a. So as you can see over there, from minus a to a, then you can compute the integral only from 0 to a and twice, and because both are the same. Now, once the function is odd, then here from minus a to a, then halfly positive, halfly negative, so that they cancel out each other, and so that the integral must be 0. Okay. Now, here let's evaluate the integral, and this is a symmetric interval, and this is even term. Now this is odd term, so that if you work with that term, then contribution will be 0. And also this is odd term, so it will be 0. So the given integral can be written, now everything is even term, so that by using that formula, we can get this one here twice of from 0 to 2 and x to the 4 plus x squared plus 1. Okay, so that we can find the antiderivative here, 1/5 of x to the 5 plus 1/3 x to the 3 plus x, and evaluating from 0 to 2. Of course, here we have to put 2 here now. Okay. And so the computation is simpler, rather than an evaluation at 2 and minus 2. Once you are putting here 0, then it's 0, so that you can save time. And twice of from 0 to 2 is much better in computation. So you can finish this computation yourself. Okay, for this one, now here, this is even, and now sine squared, original sine is odd function, but squared is even function, so that overall, this is even function. So you can write this one here, twice of integral from 0 to pi over 2, and 2 cosine theta, and 1 plus sine squared theta d theta. Now, we have to use a change variable, I mean a substitution, to make it simpler. Okay, let's start with u equal sine theta, because we have cosine theta, so that now we can choose sine theta. Then here and du equal derivative of that one, that is cosine theta, and d theta. Right? So this portion is now du. Okay. Now we have to find the lower bound and upper bound for u. So theta equals 0 implies that now sine 0, which is 0. Now here theta equal pi over 2, then now sine pi over 2 is 1, so that u is 1. So the given integral is the same as now twice, and from 0 to 1, 2 stay there, and this one, for that one, we now change the lower bound, upper bound for u. They are 0 and 1, yeah. And here we have 2 is here, and divided by 1 plus u squared. And now cosine theta d theta is du. Okay, let's rewrite this one. 2 comes out, so therefore integral from 0 to 1, 1 plus u squared, and du. Okay. What is the function such that its derivative is 1 over 1 plus u squared? Can you find it? that is arctangent u, right? So that is same as a force there, and antiderivative of this one is arctangent and of u. U is from 0 to 1. Once u equals 0, then the value is 0. Once u is 1, then that is pi over 4. So that 4 times pi over 4. So the answer is pi. Okay. Now we'll go to this problem. Okay, this is even term, and sin x is odd. So their multiplication is odd. Now, this is a symmetric interval, an odd function, so that the value must be 0. And at this level, and by using the techniques you have learned, you cannot get antiderivative of that one. But later on, when you are working on chapter 8, then you will be able to get antiderivative. Even though you can get antiderivative, the result must be 0. It's an odd function, symmetric interval, so it must be 0. Okay? We'll continue in the second part. Thank you.